We're going to talk today about something called the rational root theorem. Now, last year, you found roots by factoring. You could call them x-intercepts, solutions, zeros. They had a whole bunch of different names, but they were basically roots of quadratic equations. So last year, when you had a quadratic equation like x squared plus 5x plus 24, remember you found all the factors of negative 24, and you were looking for that special pair that added to a positive 5. We found that pair in our negative 3 and positive 8. So I broke my equation down into two factors, x minus 3 for the negative 3 and x plus 8 for the positive 8. Then we had to split them. In order for two numbers to be multiplied together and be equal to 0, one of those two numbers has to be 0. So if x minus 3 was the one that was equal to 0, x had to be 3. And if x plus 8 was the one who had to be equal to 0, then x had to be negative 8. So we had two solutions, or in other words, roots, that were positive 3 and negative 8. What happened if you couldn't factor an equation, or if you didn't know how to factor that particular equation? For instance, what about something massive like 5x to the 7th plus 4x to the 5th minus 3x to the 4th plus 8x squared plus 7x plus 3? This is a problem because I don't know how to factor something this large. Well, the rational root theorem is going to help us out. The rational root theorem says if the polynomial, we're going to call it p of x, has integer coefficients, then every rational root of the polynomial equation p of x equals 0 can be written in the form p divided by q, or p over q, where p is a factor of the constant term and q is a factor of the leading coefficient of p of x. Does that make perfect sense to you right now? You mean it doesn't? Oh, well, let's talk about that then. Let's start with a polynomial. First thing you're going to do is identify the constant and the leading coefficient. The constant in this case is a positive 6. Our leading coefficient is 2. We're going to then identify all factors of the constant and the leading coefficient. Factors of 6 can be positive and negative 1, positive and negative 2, positive and negative 3, and positive and negative 6. Factors of our leading coefficient 2 can be positive and negatives of 1 and 2. Remember, we're going to have to use positives and negative factors on using rational root theorem. So to identify possible rational roots, this will not, some of the roots we come up with will not be actual roots for our equation, but we're going to find all possible rational roots by taking the ratios of all the factors of our constants over all the factors of our leading coefficients. Let me show you what that looks like. If I take all the factors of my constant and make all possible combinations of putting them over the leading coefficient factors, I'm going to come up with a whole bunch of fractions. I'm going to have positive and negative 1 over positive and negative 1 and positive and negative 2. Now, each one of these is going to make their own factors. I'm going to have 1 over 1. I'm going to have negative 1 over negative 1. I'm going to have 1 over negative 1 and negative 1 over 1. That would take an immense amount of time to list all of those fractions. I'm going to simplify this just a little bit, because things like 1 over 1 become a 1, 2 over 1 becomes a 2, and so on and so forth. So when I simplify them, I get a positive 1, negative 1, positive 1/2, negative 1/2, and so on and so forth. These are all possible roots to my equation. It's kind of huge, right? But those are all possible roots. Now, some of these have been repeated, like the 1 and the 1, and the 3 and the 3. So I'm going to take out all the repetition, and it cuts my list down by a little bit. We'll talk later how to decide if these are actual roots or not. Let's try that again. We've got an equation. We're going to take factors of our constant, which is -9, and factors of our leading coefficient, which is 4. We're going to take all those together. Remember, the constant factors go on top, the leading coefficient factors go in the denominator. I'm going to make all the possible combinations of those fractions that I can. Remember, the 1 has to go over the 1, 2, and the 4. The 3 has to go over the 1, 2, and the 4. And the 9 has to go over the 1, 2, and the 4. I'm going to simplify a little bit, because 1 over 1 just gives me 1, 3 over 1 gives me 3, 9 over 1 is just 9, and so on. I'm going to get rid of any repetition if there is any. In this case, there's not. So these are all possible roots to this one little equation. To find out if they're actual roots or not, we're going to use some synthetic substitution. So we're just going to go over this briefly. We're going to go over it in more detail in class, but this is what's going to happen. You're going to take one possible root at a time. Use that number as A in your synthetic division. If you come out with a remainder of 0, that means that the number is an actual root of our equation. So just like I said, pretty quickly, let's try out this positive 1. If I divide using synthetic division with a positive 1, I get a remainder of 0. That means positive 1 is an actual root to my equation. In other words, 1 is a root, or an x-intercept, or a solution, or one of the many other names that it can have. Then I do it again with the negative 1. This time I don't get a remainder of 0. That means negative 1 is not a solution or is not a root. We're going to continue this in class. You basically need to know how to come up with all the different possible roots to an equation. Make sure to bring your notebooks because we'll take additional notes in class this time. Have a great day.